this JMD webinar on the special issue around datasets in engineering design. This webinar is being organized by me, Faiz Ahmed, and Dr. Stefan Menzel, who is here, and Dr. Ikjin Lee, who could not make it today. And I want to thank all the organizers as well as all the speakers who will be presenting their work today about various different types of engineering design datasets. And unlike before, you will see that we have a lot more speakers today. And the reason is that there was just so many exciting topics that we thought that it would be great to provide a broader depth of broader coverage of different data sets that are being presented. So just to give everyone some context, this special issue, which we had organized along with Dr. Cyril Picard, Dr. Michael Kokolaris, Dr. Wei Chen, Dr. Chris McComb, Dr. Pingfeng Wang, Dr. Ikjin Lee, Dr. Tino Stankovic, Dr. Douglas Allaire, and Dr. Stefan Menzel. So you can see we had a long list of guest editors who came together to kind of talk about this very special problem of that engineering design really requires data sets that are publicly available and are easy to share and are findable and so on. So we got a lot of interest from the community, as you can see from a long list of papers here that which have all shared their data sets. And so we thought that maybe we should talk more about it and organize this special webinar where we can have some selected talks from the special issue to give the community kind of some insights on how the authors created these data sets. With that, I want to just open the floor for Dr. Stefan Menzel and Dr. Calvin Seepersad to add some words.
Stefan, would you? I guess I'll go first. So anyway, thanks everyone for attending today. I want to really thank Faiz for organizing our webinar series in general, and to thank all of the individuals who contributed both to this webinar, but also to the special issue on which this webinar is based. So if this is your first time attending a webinar for the Journal of Mechanical Design, welcome. We try to have these webinars about 4 times a year, sometimes more. And oftentimes these webinars are focused on emerging issues of interest to the audience or special issues that we've organized in our Impress. So this particular special issue, I really want to brag on the organizers of this issue. I think this was a new take on special issues where we focused on papers that included data sets that would be of service to the community. So all of these papers not only include your traditional referee journal article, but also an accompanying data set. And they did such a wonderful job with this special issue that we've had more submissions to this special issue than we've had for any special issue in the last couple of years. And the issue includes almost 20 papers on this topic. So I really want to commend all of the organizers whose names are listed here for doing such a great job of soliciting excellent articles and really shepherding them through the process. So I hope everyone enjoys the webinar today. And if you have suggestions for themes for future webinars, I'd be happy to hear them. Thanks.
Yeah, thanks, Carolyn. Of course, thanks, Faiz, a lot for organizing this webinar. So actually, I'm quite thankful also to you, Faiz, and also Dr. Cyril Picard for taking the lead on that special issue at that time when you kind of like invited me also to be a guest editor, because I mean currently in the age of the AI, where basically data is so much needed and important for all kind of tasks we are currently doing now, and especially in this exciting time, of course, now with LLMs and everything going on, the data is kind of like the fuel and the power we need to get these things going. So I was very grateful to contribute to this special issue, and I'm grateful to have been invited for supporting this. And yeah, thanks a lot today for all the speakers that you could take your time to join us here today and also present your work. we are very excited about what you contributed to the journal, and we are looking forward, of course, now to hear more detail about your work. So thanks a lot and looking forward to your talks.
Thank you. Thank you, Stefan. Thank you, Carolyn. So just to kind of quick agenda, the speakers will introduce themselves. Each speaker will speak for about 10 minutes in the order that we just listed below. And after all the talks are done, we will have Q&A. What we would encourage you to do is while the speakers are speaking, feel free to post your questions in the chat, and we can do it. We can also have them at the end. Unlike previous times when we had special like gather.town, because we had a longer list of speakers, this time we will just be on Zoom and discuss the Q&A for a longer time. Please mute your microphones, and also, as I said, you can post your questions. So with that, we can get started with the speakers. I would like to invite our first speaker, Inbam Chung, to please share his screen and get started. Thank you.
Thank you, Professor Ahmed. So I hope everyone can see my screen. There's going to be a gray thing. Yeah, it's going to go away. So originally it was the presentation was prepared by Professor Ping-Pong Wang, but unfortunately he had urgent family matters, so I am presenting on his behalf. So our research was on design for resilient transmission networks using a generative model. So I'm just going to go over the research background and then proceed the agendas from that point on. So power systems are subjects of various disruptive events. And in order to prevent the catastrophic results that may result from the disruptive events, we need to design a resilient system network in order to prevent those damages. Now, most approaches of these power system networks are mostly focusing on controlling existing networks. And you can sort of see why, because throughout the entire time, we already have these power system networks, and it is too costly and infeasible to actually just break everything down and then design a new one. But because there are cities that are being built or small regions that require a new network, we thought it would be valuable to have also a means to design a new network architecture that has an intrinsic ability to sort of reduce the degradation of its performance in the event of disruption. Now, the problem was these power systems, because they're defined as networks with various components, it's really difficult to explore through using conventional optimization methods because they're non-numerical. They are multidimensional and they're expressive matrices. So a good way of these kind of situations are the generative approach, where we can use the generative modeling and its latent space to act as a parameter that we can sort of subject to numerical optimization methods that are already existing to design new network architectures. So there are several attempts, I believe it's still ongoing, to accumulate these data sets for electrical grids, power systems, either transmission or distribution networks. Now, the problem was in order to train a generative network, so in order to train a deep learning model, these current state of benchmarks was not enough. It was less than a few hundred, and it was just not enough to train a deep neural network based generative model. And another way we were exploring was how about using some conventional random graph models. Like there are like Erdos Renyi, Barbasi, Albert, and Watts-Rogatz each have their own method of creating random networks. Now, the problem was these network, or more or less, they are graphs, random graphs, are not specifically designed for power systems. So although it creates topologies of interesting or realistic networks, it doesn't fill them in with appropriate components. And you might ask, okay, but if we can generate random networks, then why train generative model? Again, that would be because we want to subject with design optimization networks, the design optimization methods, so that we can sort of have a controlled environment for like data latent space, rather than simply just creating random graph models for instance, random search in the optimization approach. So moving on to the data structure and construction. So we created in total about 9 sets. Obviously, these can be actually just merged into a single data set of larger size to train a huge model. But at the moment, we are trying to, one by one, and it will be more presented in detail in the later slides. But to summarize, each dataset consists of bus branch, which is node and edge information to represent the topology of the power system and its components, for instance, the generators or its connecting lines, its loads. And each grid is generated using a open source grid generation algorithm called SymGrid, which is based on MATLAB. And also, after generating the synthetic grid, it is also subjected to another open source toolbox called MapPower in order to calculate all the electrical simulation results. The data size were actually determined to enough for it was arbitrary, but enough for training the deep learning models. And the analysis methods, which are indicated as ACPF, DCOPF. I'm going to go briefly on those, but it's methods, analysis methods for electrical simulations. They were determined to sort of ensure the feasibility of the generation time. So an overview of the generation processes, the SymGrid toolbox randomly sort of generates a initial topology and then moves on to assigning transmission line properties and based on distributions of the transmission network. And then it goes on to assigning the bus types based on real world power grid distributions, and then the generation capacities for the demands. So basically, it creates topology and fills them with electrical components. And then moving on, we after the data set is generated, we move on to executing the electrical power simulations using the power flow and economic dispatch. Basically, it means if there are generators here, and there, and their loads of different magnitudes, what is the most efficient way of distributing and generating power and then distributing them. So after the simulation is executed, we collect the bus branch generator information from the synthetic grid, analyze it, execute map power simulations, and then accumulate them accordingly to the bus information, branch information, and generator information. So that in the event another engineer wants to execute by altering perhaps the designs, they can also execute this optimal power flow simulation if they want to. So as I said, each data point, I guess, consists of branch, bus, and generator information. Basically, the branch is all the edges, so it contains the topology information and these line properties, and for the bus, load gen and slack buses, those types, all these power system characteristics are required for the optimal power flow. And if we are only considered for the design, mostly it's basically this bus connection information that contains the topology information. In order to ensure that the data sets are not some randomly generated, but rather somewhere within feasibility and realistic looking. We sort of compared with existing benchmarks, very frequently used IEEE 57, 118, and 300 bus systems. And you can sort of see I compare with mean and standard deviation. Now, there are values that are very largely different. I mean, there are values that are somewhat similar, but values that are largely different. But you can sort of see that the values within the parentheses are the standard deviation. So it's really hard to represent all these, whether a design covers the data set covers all the designs, but you can sort of see that the standard deviation is well within the boundaries of the IEEE benchmarks, as well as it is still feasible amount of data, feasible designs within the data set. So the main topic was to utilize these data sets to create generative models for the power systems in order to execute the design optimization. So what we utilized was the GAN model, very frequent. I'm pretty sure many are familiar. So the data set is sort of structured like this. The line data, which is the transmission line data, is N is the number of data sites, and the number of buses, which is the number of nodes. CI and CM are the number of classes for each for lines and nodes. So you will see in the future slides that it contains sort of the information about whether it is a generator, how big of a generator it is, or the line transmission line capacities and all that. And very other parts are very standard generative GAN model components, the discriminator, which learns the network representations using the graph convolution layers. It's one of the ways of integrating learning representations for network data. And then after everything is trained, we basically just use the latent space as the design variable and the generator to create the graph network power system network. So after everything is trained, this light blue marked region is the only component that we actually use. Now, in order to validate that the generated data set, so basically not the data set itself, but the data, I guess the samples that are generated using the trained generative model are also validated. And I'm going to have statistics on the next slide, but you can sort of see that there are different distributions, but well within with a certain amount of ranges. So the generated sample set using the generative model does not go like well beyond the training samples, but still they sort of consist of different distributions, sort of having the feasibility and diversity for the generative framework. So these are the statistics for this. Once again, the average are within the values, and the values within the parentheses are the standard deviation compared with training data, which was the data set that I've described in the previous agenda. And the sample 1, 2, 3 are basically just samples that are generated using the generative model using different parameters. And you can sort of see that they are within, they have similar average but still have some diversity within the feasible range. And moving on to the optimization of the power system networks, basically we utilizing four different steps. Step 1 was to create the data set, and then step 2 was to execute the power system simulations in order to create the data set. Now, the third step was train the generative model, which was the last agenda, and the final step is to utilize the train generator to implement an optimization algorithm integrated with the optimization algorithm using the latent space as design vectors to create optimal performing power system network. Now, in order to say optimal performing power system network, we have to have like quantitative measures for resilience, which was the objective of this research. So there can be two aspects of quantitative measuring the qualities of these networks. One is the topological aspect, measuring how well the network is resilient in topology aspect, and the functional is regarding the electrical property. So we use three measures in order to measure them. Two are the topology related, which is utilizing the centrality. So it's these two are a little bit similar. So what they measure is how well they are connected, but what happens if one gets removed. So basically within the topology, we calculate all the shortest paths and how it represents how well they are connected to each other. The transmission line loading is basically the logic behind is if it's loaded to the maximum capacity, if there is some event, a disruptive event, there is no room for more flow to go on. So having a lower average of line usage is better for a resilient system. So within the optimization loop, we do random sampling based on this normal distribution and then put it into the generator and then evaluates performance, and this loop goes on and on until a convergence criterion is met. And as I mentioned before, this central between the centrality is better when it's the values are lower, and it's efficient network efficiency is better when the values are higher. And you can sort of see we compared it with IEEE 57. That's the case study that we did. Random sets have these kind of values from set 1, 2, and 3. Those were the presented ones from the previous slides. And then PG is just for short for guided generation. And you can sort of see that it has the lowest value of between the centrality and the highest value of network efficiency. So topology-wise, it does work. This optimization framework does work, and the generative model is able to create feasible designs that are performing better than the original benchmark. Now we also want to use the guided generation for the encompassing the functional aspect as well. So there are two methods. Basically, the one better performing is the nested approach, where I execute the power simulation within the optimization loop, and you can sort of see that once again, comparing to the original network benchmark, you can sort of see that the overall performance, they all perform better. The optimization was able to perform better in most of the aspects. So to conclude the research, I hope I haven't talked too much. We created a generative model framework in order to optimize a power system network. And the future work is basically fully utilizing the information. So I haven't, while the data set consists of all these informations, for the generative framework that I presented just now, we are not currently using every information that is available. So that is one of the things that I'm trying to do right now, as of now. Another is tackling an expansion problem. So instead of having from scratch, because in that case, we can only utilize this framework for completely new networks. It is beneficial if we can sort of have a small subset network and then use this framework to expand the network, adding a certain number of nodes and evaluating where it will be most beneficial if we add these nodes in particular locations. And that is basically the two main focuses of our future work. Thank you very much for this opportunity to present for this webinar. If you have any questions, please feel free to ask them. Thank you very much.
Thank you. We can have the next speaker, please. Yajit Khan, Comlet. Please go ahead.
Hello, everyone. Is anyone able to see my screen? Well, Yes, I got a thumbs up from Faiz, so I'll get started. Hello, everyone. My name is Yi-Jan Chumnik. I go by Yido for easiness. And today I'm going to be presenting a work that I did during my transition from my PhD to my current job at GE Aerospace. This is a collaborative work that we did with GE Aerospace at that time with my colleagues, Drs. Sandeep Ravi, Piyush Pandita, Sayan Ghosh, Liping Wang, and also my advisor, Professor Dr. Wei Chen. The talk is titled Heterogeneous Multi-Source Data Fusion through Input Mapping and Latent Variable Gaussian Process. So what is multi-source data fusion? What do we mean by that? So I asked the Bing AI to give me an image on multi-source data fusion, and I think it gave a good representative of it, saying that you get data from different sources, whether it's computers, experiments, or different measurements, and you try to build a data fusion model where you fuse all the data together to get a global or a universal model at the end, in the middle. So it's basically the process of, again, combining different information from different sources to have a more accurate, comprehensive, and reliable representation of what you're trying to represent. It can be underlying scientific phenomenon, it can be a design system, or anything that you're interested in. So the goals are basically exploiting the strength of each source while also compensating for their individual weaknesses. And again, at the end is to get a very accurate model for any engineering system that we're interested in. However, there can be some significant drawbacks and challenges, such as we don't incorporate usually the underlying procedures, processes, variabilities that are associated with these sources when we model them together. And this can be anything from different materials, different fidelities, different experimental conditions. These are some of the things that we usually tend to not put into our model when we fuse them all together. And again, when we collect the data and put them into a single model, we don't tend to differentiate the models specifically in the model. So we put them into a table and then feed it to our model, but the model doesn't know what data comes from which model or such. And finally, the sources can contain different inputs. That's where the term heterogeneous is coming from, meaning that one can have 2 design variables, the other one can have 4. They might share some, they might even have completely different design variables and whatnot. So to solve all these challenges, what we propose in this paper is a framework called heterogeneous multi-source data fusion with input mapping calibration and also latent variable Gaussian process. So first I'll go into what our underlying model, the latent variable Gaussian process, is, and give you some examples of how it works. So the latent variable Gaussian process, what we abbreviate as LVGP, it allows us to combine numerical variables and categorical variables into a single model. Traditionally, especially for GP models, it's a bit unclear how we incorporate categorical variables into the GP model, but LVGP allows us to do such modeling. So we go from having an output Y with an input X that is numerical or continuous to modeling a system where we have output Y and an additional categorical variable, which we call T. So what LVGP does is, given some categorical variables, which can be different shapes, so for example, a triangle, a circle, or a square, what it does is it maps these categorical variables into a numerical space. So what we know is that these categorical variables must have some underlying, possibly high dimensional numerical variable space, right? So that they can be represented in a numerical way. What LVGP does is, by using dimensional reduction techniques, it reduces this high dimensional space into a 2-dimensional latent space, where we have two now numerical variables that represent each category, each categorical variable. And once we have numerical variables for these, we can combine them into a GP model, like how we do it regularly, and model our system. And then what we call these latent variables as our Z variables, just for sake of noting. So in a standard GP model, where we have a mean function for the continuous variables and a correlation function for them, what we do is we try to estimate, we do some maximum likelihood function estimation to get the hyperparameters, such as the length parameter that we see here. But within this mixed variable LVGP, where we have numerical and categorical variables, we also, in addition to our parameters, we also estimate what these latent spaces are as well. So during the training, our model learns what this two-dimensional latent space looks like. And this is important because, one, it gives us a categorical numerical mapping, and this learned latent space gives us some physics or underlying physics or underlying physical meaning of these variables. What's the relationship with them? How do they influence the output? As such, it gives us some interpretability about the system that we're interested in. And in addition to these advantages, just like any GP model, it gives us uncertainty quantification that we can use for data fusion, Bayesian optimization, and active learning in the future. So how do we use LVGP for multi-source data fusion? We assign, in addition to having the common variables, we assign another variable, a source variable, to each source. So if I have some x's from source 1, I assign a categorical variable to it. If I have some x's from source 2, I assign another categorical variable to that source. And then during the training, we map these sources into the latent space and try to capture the relationships in the latent space. And as a result, we can get an accurate model. So let's consider we have 5 different sources of data, which has their own representation or own different meaning, own different inputs and outputs. We can map them into our latent space and then and then finally learn the correlations between them to get a single unified GP model that can make predictions on all of the sources and make predictions and learn the relationships between the sources specifically. So overall, representation-wise, we have different sources, and then we can add another categorical variable, which is we call S here, to that source, and put them into the LVGP model to get an accurate response prediction and also interpretability from the latent space to see how dissimilar the sources are, how similar they are, and whatnot. So these are the 2 main advantages of LVGP. So right now I'll give it a quick example for what we did for fecal alloys. Here we collected data from different sources. We have our reference source. We call this as GE data. This is where we collected at GE Aerospace. And this is the repeatable source, credible source that we take as our reference. And we have 11 features that we collected from this data. I'll just note that here that all of the features right now are same for all the sources. So we're modeling the same X's, and we try using these 11 features. We try to see how LVGP performs compared to a multi-source GP, where the model has no differentiation between the sources because we're not tagging anything to the model. And we try to model the hardness change for the material strength. And what we saw was that the multi-source GP leads us a response surface that we see here, which has some peaks and valleys, which is not very ideal for our materials. And it gives us high prediction uncertainty, and it doesn't make any source-specific predictions. So for example, if I want to make predictions on GE data, I can't do it because the model is not aware of it. However, for multi-source LVGP, what we see a very smooth response surface, low prediction uncertainty, and also we can make source-specific predictions. For example, I can make predictions on the source Kim or the source GE data, and I get better accuracy in those predictions, which leads to better materials design and whatnot. And again, we said that we map the categorical variables, the sources, into a latent space, to 2-dimensional latent space that we see here, and we can differentiate how the sources are closer to each other, similar to each other, and or how different they are from each other. And then what we noted here is that some sources lie very close to our GE data, our reliable source, and some are very further apart from each other. We don't know what's the difference causing them because we didn't conduct the experiments. But what we can do is actually we can remove these further sources from each other so that we get a better model, and that's what we observed in our previous study. Once we observe, so what we're saying is that not all sources are helpful. We can remove the unreliable ones, possibly unreliable ones, and get a better model. So I now get to the heterogeneous part. That was the previous example was a case where we have all the same, they share the same input space. However, a lot of sources, they do not share the same input space, and that's why we call them heterogeneous. And these differences can come from designs, fidelities, or complexities. I'll give a quick example. Let's say we want to design a beam, and we're interested in the deflection of beam, and we can have a rectangular beam with 2 variables, a hollow rectangular beam with 4 variables, and also a completely different design, a circular hollow beam with 2 different variables that has no intersection between them. So it's, with the traditional GP models, at least, it's kind of impossible to combine them into a single source because, or single model, because you don't have a shared input space. So what we do is basically map all these sources into a common reference space, so that we can model them all together. And that's the first step in our approach. We map them through a technique called input mapping calibration. This was some method proposed by CU Ta and Professor Chen back in 2019. And here's the pretty much basic idea. Let's say we have a rectangular beam as our first source, and we select this as our reference source because it has the highest data availability. We'll see why this is important in a second. And what we're interested in is how can we map the hollow rectangular beam, which has 4 variables, into this 2-dimensional rectangular beam space. So we're saying is that x2, which is the hollow rectangular beam, can be mapped to x1. And to do this, we're defining a linear mapping function g. So we need to find a and b such that when we plug x2 into it, it will give us some representation in the x1 star or x1 space, which is a 2-dimensional rectangular beam space. So the way we do that is we first build a GP model on the reference source. This is the highest data availability. The higher the data, hopefully the more accurate the model is. So we're saying is that for any x1 star, which is the mapped x2 I put into that function, it should give me the same output as the original y2. Here we can do this because the y1 and y2 are same output, the deflection of the beam, but it's just coming from different sources. So by minimizing this difference between them, we can get a mapped x2 variable, which has some coefficients a and b. So whenever I have a new x2 design, it can be mapped into H and B space. So once we can do the same thing for the hollow circular beam, map them big R and small r to HB. And once we have that, we can add additional categorical variable to each source and build our LVGP just like how we did it before. A quick example will be an ellipsoidal void application where we have different sources across fidelities and complexities. Here we have a 2D ellipse source, which is represented by 2 variables. It has 2-dimensional, it's an elastic simulation and has a lot of variables. We have a 3D, we can extend this to 3D, a different complexity, and it has 3-dimensional variables. And also we can extend this to another case where we add a rotation to this ellipse, and also do plastic simulations, which is much different than the elastic simulation. So it's a difference in fidelity. What we're interested in is we have low data for this case because it's expensive, it's the highest fidelity. We only have 10 samples. So what we're interested in is by combining the information from these 2 sources, can we get accurate predictions on this model itself? And that's what we observed in our results, is that multi-source LVGP compared to 2 other models, the first one being a multi-source GP, where we map all the inputs to a same reference source, but don't differentiate them through the GP model. Or why don't I just take only the data in this, build a GP model, and test it on that? So compared to both models, what we see is that multi-source LVGP provides much better error predictions, lower error predictions for the system or for the source that we're interested in. So in addition to that, we can get some interpretability about the system of interest, meaning that the latent space learned from this model tells us that the 3D rotative void, which is the highest fidelity or different fidelity, is laying in a different space than the other 2 sources. And this is because these are plastic and these are elastic. So the main difference comes from elastic plastic simulations. We did a similar example on the design example that I showed earlier. Predictions on the hollow circular beam. What we saw is that the LVGP approach gives us much lower errors compared to multi-source GP or just the GP model built on this source only. And similarly, the latent space captures these relationships very well. For here, they're dominated by the rectangular shape, whereas the circular hollow beam is laying further apart. And finally, this is an example where we combined, where we're interested in the yield strength of a material that is produced by different manufacturing modalities, such as laser powder bed fusion, electron beam welding, and friction stir welding, which share different variables. And what we saw is that LVGP once again gives us a better predictions on the source that we're interested in. However, we are very cautious with this results in a sense that we have only 3 samples to train our model, and we don't have a lot of samples to test our model. Although we're getting good results, it might not be, we're not very confident in it in terms of the accuracy, let's say. And then latent space also tells us something, that the friction stir welding is much further apart and the other 2 sources are closer. And this could be, we are hypothesizing that this is due to the high energy manufacturing process employed for both models are similar for these 2, whereas for this one. So I think I'm a bit over time, but in conclusion, what we contributed here is that we can get accurate data fusion modeling for low data scenarios with heterogeneous sources. This model also has all the advantages of Gaussian process, uncertain quantification, adaptive sampling, and we try to address the practical engineering challenges such as inconsistencies in experiments, different simulation experiment settings, and also low data scenarios. So with that, I'll conclude my presentation. Thank you very much, everyone.
Thank you, Ido. Now I would want to welcome Dr. Nambu Khan. Please.
Okay, so can you see my screen?
Yes.
Okay, hello everyone. My name is Namu Kang, and I'm excited to present our work titled Deep JEP 3D Deep Learning Based Synthetic JEP Engine Bracket Dataset. This research was a collaborative effort between Narnia Labs and KAIST Smart Design Lab. Here is the outline for today's presentation. I will start with the background, explaining the motivation for our work. Next, I will introduce how we generated the dataset, followed by how we performed the dataset validation. Finally, I will conclude with the key takeaways of our research. Let's begin with the core challenge that motivated our study, data scarcity in engineering. As the chart shows, compared to the field like NLP, computer vision, which have massive data sets, the engineering domain suffers from a lack of large-scale, high-quality data. For instance, the SimZap dataset, a well-known benchmark for jet engine bracket, contains only 381 samples. This limited size poses significant challenges for developing and testing robust engineering AI models. To address this bottleneck, we developed Deep JEP, a large-scale synthetic dataset. Our solution is a comprehensive data generation workflow, which I will explain in detail. Through this fully automated pipeline, we created a dataset that is 5.6 times larger than the original SimZap dataset. It is not just larger, it also richer, containing over 209K detailed node level data points per sample on average. Now let's dive into the specifics of our dataset generation process. The process begins with step 1, seed data selection. We started with the 381 samples from SimZap and filtered them to ensure quality and consistency. We removed about 100 samples that had geometric issues, such as internal cavities or boundary alignment errors, which could cause instability in the simulation pipeline. This left us with 263 high-quality CAD models, to serve as the seed for our generative process. In step 2, shape generation, we employed an implicit neural representation model, especially on autodecoder architecture of the SDF. This allowed us to generate about 4,800 new diverse bracket designs by interpolating in the learned latent space. However, generative models can sometimes produce irregular geometries. Therefore, step 3 was shape filtering. We identified and removed about 2,000 geometries that are tone or had disconnected regions, ensuring they were physically viable for analysis. And this resulted in 2,700 well-formed shapes. Next, in step 4, FEM simulation, we established a fully automated pipeline to label the engineering performance of these shapes. We perform 4 linear static load cases: vertical, horizontal, diagonal, and torsional, as well as modal analysis to find natural frequencies. This automated process wasn't perfect, so we encountered about 200 simulation failures. Furthermore, in step 5, outlier removal, we filtered out about 400 samples with unrealistic stress values caused by mesh artifacts. And after that entire rigorous process, we finalized the DeepJEP dataset with 2,138 samples. And here is the result, the DeepJEP dataset. This gallery showcases the diversity of the generated brackets. DeepJEP provided far more than just geometry. For data quality, we used second-order tetrahedral elements for higher precision, resulting in an average of 130,000 elements and over 209,000 nodes per sample. The data categories is extensive. We provide geometric data like step and SDL files, scalar data such as mass and maximum stress, detailed field data for every node. Even rendered the image from 26 different views to support research on multi-view models. Now I will discuss how we perform the dataset validation to ensure its quality and comprehensiveness. Our quality assurance had 2 parts. First, for performance data verification, we identified and removed the simulation outliers using the IQR method. The initial dataset shown in plot A had a long tail of unrealistic stress values. After filtering, plot B shows a much more uniform and reliable distribution. Second, for geometrical feasibility, we ensure the final mesh quality was high. We checked the metrics like the aspect ratio and find that only about 1% of mesh element exceeds the recommended threshold for stress analysis, confirming the dataset's integrity. And next, we performed the diversity check. To visualize and compare the design diversity, we used beta VA to reduce the dimensionality of the shape into a latent space. This scatter plot clearly shows the latent space for both data sets. The dark orange point represents the original SIMJAP samples, while the light orange points are from our DeepJEP data set. And it's evident that DeepJEP provides an expanded, denser, and more diverse design space, which is crucial for training more generalizable AI models. To demonstrate the practical value for DeepJEP, we conducted a case study on surrogate modeling. we trained the surrogate model to predict structural performance based on the 3D shape. When trained on DeepJab, our model achieved average R-square of 0.967, 3.2% improvement over the model trained on SimJab. Furthermore, MAP was reduced by a massive 72.3%. These results powerfully demonstrate the superior quality and utility of our synthetic dataset. This brings me to the conclusion of my presentation. In conclusion, the DeepJab dataset addresses the critical issue of data scarcity in engineering. It is 5.6 times larger than SimJab dataset and provide more accurate and comprehensive data. And as a result, DeepJab is already being used in the research for tasks like surrogate modeling and design optimization. So it is well positioned to become a standard benchmark for evaluating engineering AI models, opening up new research area like generative AI. The potential applications are extensive. With DeepJab, we can implement AI-driven design process. Let's take a look at the video. You can generate thousands of concept designs, and you can explore generative design and predict the engineering performance in real time. Or you can cluster them according to the design similarity. You can filter them. You can compare your design with the data. And if you input our target performance, you can get optimized design by generative AI. Or you can share the good design with your team members. And finally, you can interpolate new design between the good design candidates. Thank you very much. Thank you for listening. And DeepJab dataset is accessible through this QR code and URL.
Thank you, Namu. Now, our next speaker will be a joint talk by Dr. Binyang Song and Dr. Chris McComb. Please take it over.
Yes, let me share my screen. Can you see my screen now?
Yes.
Yep.
Maybe if you want to do full screen.
Yes. How about now?
Yes, perfect. Thank you.
Yeah. Good morning, everyone. I'm Binyang Song, an assistant professor in the School of Mechanical and Aerospace Engineering at Nanyang Technological University. Today, I'm excited to introduce HAVA, the High-Form Uncrewed Vehicle Engineering Repository, a multi-modal dataset developed to support design and AI research in UAVs. It's a collaborative effort with Abiram Carey from Virginia Tech and Gary Stump from Penn State. One of my co-authors is also here with us today. Chris, would you like to introduce yourself and start us off?
Absolutely. Thank you so much, Binyang. I'm Chris McComb. I'm an associate professor at Carnegie Mellon University. It was a great pleasure to work with Binyang, Abi, and Gary on this work. Next slide. So today, we'll give a little bit of background on the high-form platform in general. We'll talk about how this specific data set was collected, and then I'll turn it over to Binyang to talk about how this data is organized, how we've extended it, and some of the potential applications that it can be used for. So this all focuses on the high-form platform. So this platform has been used extensively for different human subjects research activities. And in this platform, there are 3 different roles that people might perform. So they might be in the design role, where they focus on the construction and design of individual drones. They might be in an operations role, where they figure out how to route those drones around a town to make deliveries. Or they might be in a business role, where their task is making sure that this drone delivery business is able to turn a profit at the end of the day. Next slide. So there are a few examples now of the environment that people are actually working within. So this shows the drone design environment. So we have a simple quadcopter shown here, but we can add wings onto it, as well as additional rotors. There's a lot of design freedom in the configuration of the drone itself. We can also do physics-informed evaluation, and that was a very important labeling process for the data set that we're sharing today. In addition to these core drone designs, next slide.
Yes.
So in addition to the core
Alright.
drone designs, we have some basic AI functionality that's based on a string grammar, and we'll get into more of that later. We also have an operations role on the next slide. So in the operations role, individuals were tasked with determining how to route drones around this town to make deliveries. And there were often cases where you need drones that are capable of flying far with weak loads, or flying shortly with extremely large loads. And then the final role on the team was business. And that business interface is shown on the next slide. For people in the business role, they essentially were in charge of identifying which operations plan was most effective. So we gave them some simple capabilities that look pretty comparable to the operations interface. But what was great about building all of this from the ground up with a team from Penn State Applied Research Lab is that we were able to fully instrument this platform. So as participants work within their team, we capture every piece of information about the actions they take, about the designs that they create, and also about the communication that takes place within the team. And in prior work, we've shared a few of the outcomes from this through other data sets. And this highlights some of the results and the potential from human AI teaming. So we know that when we use AI as a tool, teams do better, but they also act a little bit differently. So there's a different human focus. We see broader exploration. We've also learned through this interface, next slide, that when we use AI as a partner, human teammates can actually take on a significant adaptation burden, but that design of interaction needs to be very precise. Finally, we've also shown that you can use AI as a coach. And when using AI as a coach, there's a lot of potential. But again, it really comes down to the specific details of that implementation. Next slide. So within the context of all of this, we're going to be taking a look today at the drone design data set. So this figure is from some of our prior work and shows a bit of this design space. So we have some pretty distinct regions, pretty distinct types of designs that come out in this design space. And what Binyang is going to be getting into now is only a subset of this entire potential, because we wanted to provide something that was representative, but also lightweight. So Binyang, over to you.
Thank you, Chris. Yeah, this dataset includes 6,051 unique UAV configurations. Each configuration is represented in multiple formats, including a grammar string that captures its structural logic, an RGB image for visual reference, and a GLB file for 3D geometry. To complement these, we also provide natural language descriptions that highlight the key features of each UAV. In the following, I will introduce each representation format in detail. This slide illustrates our grammar-based representation, which is defined over a structured grid design space. UAV components are positioned at grid nodes and connected through links across these nodes. The grammar has 2 main parts, one for components and one for links. Each component begins with an asterisk followed by an identifier, which is a lowercase letter, and then a pair of capital letters indicating its grid position. These letters are the IDs of the rows and columns of the grid layout. After the position, a digit specifies the component type following this mapping, and the plus and minus signs indicate its size. For the links, each link begins with a caret, followed by two lowercase letters that are the identifiers of the components being connected. This structured format allows us to clearly define the topology and attributes of each UAV in a compact and interpretable way. The image representation shows each UAV configuration from a top-down perspective. Each image is a 512 by 512 pixel RGB file. In this visualization, symbols in different colors and shapes represent different components. The size of each component is proportional to its actual size. This visual scaling helps machine learning models more effectively recognize and learn the structural features of each design. The 3D mesh representation captures the full spatial structure of each UAV and is provided in GLB format. Each file includes a list of vertices with their 3D coordinates, along with a set of triangles that define the surface geometry. Each UAV configuration is also accompanied by a set of metadata descriptors written in natural language. Specifically, the design descriptor summarizes the UAV's structure based on its configuration. The performance descriptor explains how the UAV performs based on simulation results. And the operational descriptor describes how it performs with varied operating conditions. Each configuration in the dataset is labeled with the design parameters and the performance metrics. The performance metrics such as flying range, payload capacity, and velocity are obtained from multi-physics-based simulations. For flying range and velocity, performance curves are provided by increasing each UAV's payload capacity from 0 until the UAV configuration is unable to result in a successful flight. Among all the representations, the mesh, image, and grammar string each capture different aspects of a UAV design, like 3D spatial structure, 2D visual appearance, and grammatical structure, respectively. According to the predefined rules, these representations are fully interchangeable. That is, we can generate the exact mesh and image from the grammar string and vice versa. The text descriptors complement the other representations by providing a quantitative description. These multimodal representations open up broad opportunities for data-driven UAV design. First, they support the development of both unimodal and multimodal surrogate models that can predict UAV performance as an alternative to costly multi-physics simulations. By comparing unimodal models across different representations, we can assess which ones are most informative for prediction tasks. Multimodal models further allow us to explore how combining different modalities might complement each other and improve prediction accuracy. Moreover, these multimodal UAV dataset enables diverse generative design approaches across image, grammar, and 3D mesh formats. Unconditional generative models such as GANs, transformer-based models, and diffusion models can be trained to generate new designs. For example, the design AI Chris mentioned in high form was a recurrent neural network-based generative model trained on the grammar representations. The negative examples are provided in this dataset as well, which help identify and avoid flawed designs, improving model robustness. With performance labels and natural language descriptions, the dataset also supports performance, test, and sketch-guided generation. Human designers can express their design ideas in these prompts, and the generative models can help embody the design ideas very efficiently, enabling human AI collaborative design. To wrap up, our work presents a labeled multi-modal UAV dataset, which enables the development of diverse surrogate and generative models for data-driven UAV design. The dataset is publicly available on Hugging Face. You can find it via this link or the QR code shown here. Thank you for your attention. We are happy to take any questions you have for this dataset.
Great. Thank you, Binyang. Thank you, Chris. Let's welcome our next speaker, Oluwatoba.
Hi, everyone. I am Oluwatoba Fawumi, and I'll be talking about my work with Professor Saman Agamuge, Dr. Daniel Berg, and Professor Katia Tauto on land language models for predicting empathic accuracy between a designer and a user. We've seen in the design process over time that data-driven approaches have actually helped to make the whole process easier. We've seen it through user understanding, using online reviews, artificial empathic design researches, and even in ideation process. However, we know that the design process, especially the human-centered design research process, actually involves very rigorous, time-consuming, and human-intensive tasks. And this also has impacted ability to also do it in a large population, especially because of ethics and also getting participants. So the motivation of our research basically was to, if we are going to use data-driven approaches, because we know that it will result into easier and faster empathic design research, are there concerns that we should really focus on? And how to do that? So basically looking for potential limitations in using data-driven approaches in empathic design. And the first that comes to mind would be datasets, because there's really no publicly available datasets when it comes to empathic design, especially interviews dataset. And so we present a dataset from interviews with users, basically from an empathic design research. And then after the interviews, the users carried out the empathic tasks, whereby they rewatch the video of the interview they had with the designer and then post the video using the empathic accuracy approach. And pause the video and write out their thoughts and feelings. And then random selections were made from those videos, the entries of the users, random selections were made. And then the designers were asked to watch the same videos, and the videos were paused at the time where the user paused the video. And designers were given the task to guess what the thoughts and feelings are. And then the entries between the users and the designers are rated by external raters. And this data is actually what we released in this research. So the data set is consisted of different entries. We have the interview unique identifier. That's basically because the data set has about 46 different interviews, but about over 400 entries of users' entries and designers' entries, and their respective, the timestamp, the respective users' thought or feelings, the designer's guess, the rater scores, because there are 3 different raters, the empathic accuracy score, the user's emotional tone, the designer's guess, and the emotional tone accuracy. However, in order to investigate this data set with respect to current or generic data set already available, we compared our data set with the STSB data set, which is actually the semantic textual similarity data set. And the reason for us doing this is because the concept of the empathic accuracy task is to compare the user's entry with the designer's entry, which is very similar to the STSB data set or any other semantic textual similarity tasks used in natural language processing. And compare our data set first. If you look at the first image shown, the token distributions above is for the empathic accuracy dataset, and that below is for the STSB dataset. And we can see, if you look at the frequency distribution of the top 30 tokens, we'll see that if we compare that of the empathic accuracy dataset with that of the STSB dataset, looking at the empathic accuracy dataset, we see that there are specific words that are relating to that. Basically, looking at those words, we can be able to point out and say, oh, this is the concept of the discussion. You can see think, we can see drive, we can see questions, we can see car, we can see like some certain words that is specific to the scenario. However, looking at the STSB dataset is very generic, just man, woman, dog, like very generic words. Also looking at their part of speech frequency distribution, we see that for the empathic accuracy dataset, the noun and verb ratio is balanced, or let me say relatively balanced, because we see 37.9, we see 37.7. However, looking at the STSB dataset, we see the imbalance in the noun and verb ratio. We see 64.3, we see 19.4. And the ratio of the noun and verb can actually impact models when they begin to train, especially when we're talking about large language models. Also looking at the length of the sentences that are in the benchmarks or in the dataset. We see that in the empathic accuracy dataset, which is that above, we see that 56% of dataset have 15 words or below, less than 15 words. However, about 83% of the STSB dataset has like the number of words are 15 and below, which is like way more. That means the STSB dataset has shorter text or shorter sentences. And then using a model that was trained on shorter sentences to implementing such a model on larger sentences could impact the efficiency of the model. And finally, also looking at the similarity in the lexical structures of the sentences. So because we have the designer's text, or designer's utterance, we have the user's utterance, or designer's guess, user's guess. And then looking at the sentences between the two, we see that about 8% of the empathic accuracy data set has similar words between what the designer guessed and what the user reported. However, looking at the STSB dataset, we see that 59% of the dataset has about 0.5 to 1. That means a large percentage of the dataset have similar words in both sentences that was used in the semantic textual similarity task. So to further investigate because the whole concern is that if we have like a particular design research and they want to implement data-driven approach, we don't have publicly available data sets. We also don't have like data models that are trained specifically for design research. Therefore, we use just generic models. And therefore, if we're going to be using generic models, what are the implications of using generic models for empathic design research? And so we used 6 different sentence large language models. We also use different type of pooling techniques and different training approaches. So just investigating on different methods and basically trying to take out the intensive human task that comes with rating the user's thoughts and the designer's response. Basically looking at, as I said earlier, the semantic textual similarity between the two responses. And interestingly, from the study of the research is we find that different models actually had different performances with different trainings. And this actually calls for attention when we begin to sort of choose models to do, especially in empathic design, where we are sort of judging the empathic accuracy or the empathy of a designer, or judging the capability of a designer, and we're dealing with humans, so we have to be careful in like the model selection. But I'd like to just put focus on three major graphs here. First, for the SBAT, we see that that's sentence BAT. We see that for the SBAT, the blue bars or blue columns are the trainings that was done without, so just basically using the models without fine-tuning them on the domain-specific data set. Then we have the green, which is actually testing the model after fine-tuning them on the training on the empathic accuracy data set, that is domain-specific data set. And then we have the yellow bars that is actually after fine-tuning them on both the STSB data set and the empathic accuracy data set. And the reason for this is to like investigate the different models. And we see for the SBAT that as without fine-tuning on the EA data set, we see the performance, and the performance did increase or did improve after fine-tuning on the EA data set. And then after fine-tuning on the STSB plus EA data set, well, relatively, like there's like a relative improvement. However, if we look at the, oh, sorry, let me use the pointer. So I was talking about this, the first earlier. So if we look at the SIM-CSCR model, we see that without fine-tuning data sets, now the broken red boundary lines around the blue columns are basically models that, even though they had a high correlation or high performance, they had a low error in prediction. So there's the high possibility that such models would wrongly predict the empathic accuracy of the designer. So we see that without fine-tuning, so without the domain-specific data set, the model would most likely wrongly predict the empathic accuracy of the designer. However, after fine-tuning with the domain-specific data set, we see that it's improved. The error reduced, and the performance also increased, which is good. But now training on both the STSB data set and the domain-specific data set, the performance reduced. And if we compare this with the last model here, the GTE-based model, just using the model directly from the endpoint released, because there are models that have been shown to have good results in STSB, on STSB or other STS datasets. So just using the model directly, we see that it won't do a good prediction. However, training on, or after fine-tuning on the domain-specific data set, that's the empathic accuracy data set, we see that the performance is quite low compared to every other models. However, when we now do the combined approach of the STSB data set and the empathic accuracy data set, which is actually domain-specific data set, we see that the performance improved. And this just further buttresses the fact that the models are different, and because the models are different, the approaches at which we implement the models also differ in the result we are going to get. And this further also emphasizes the need for domain-specific data sets. So aside the case study that we did, there are actually other possible uses of the data sets that we sort of present. For example, data sets can be used in analyzing the designer's progressive empathic task accuracy, because it's not just a 1 point, it's a different timestamp through one interview, so about 10 timestamp for each interview. Also, it can help to improve and develop models for using large language models for design-specific tasks, as we see that it's not just all about picking a model that does well on STS tasks and directly implementing it in design research. The results would not be good enough compared to a data set that is, or a model that is trained specifically for empathic design research. And then also, the model can also be used as a benchmark, for evaluating the developed models. Basically, in conclusion, domain-specific data sets and actually evaluating the models and the method we use, really, before implementing that model or implementing the approach, is actually important in empathic design research. And that's majorly because we are dealing with humans. And so it further buttresses the fact that we need domain-specific data sets, and then also we need to evaluate our methods and models before implementing them in empathic design research. Thank you.
Thanks a lot. So now I would like to welcome our last speaker, Dr. Jengo Shah. Please take it over.
Hello, everyone. First, can you see my screen?
Yes, looks great. Thanks.
Okay. All right. Good morning. Good afternoon, everyone. My name is Zhonghui Shah from UT Austin. I'm very happy to present our special issue paper today. So basically, our data sets and experiments are used to support cross-modal synthesis, which transforms one design modality or multiple design modalities to a target modality, for example, 3D CAD model. So cross-modal synthesis is quite challenging for several reasons. For example, there is a big semantic gap between the source modality and the target modality. And of course, the scarcity of the label data for training is also another issue. And also, however, cross-modal synthesis is quite useful for engineering design, especially early stage engineering design, that which can contribute up to 70 and even 80% of a product's lifetime cost. So the research gap, at least 2 years ago, while we were working on this project, was that there were no fine-tuned models for multi-modal CAD generation. And moreover, there was a lack of data sets in support us to train a fine-tuning model. So that's the whole motivation for us to do this. And our work was motivated by answering the following two research questions. So basically, the first one is, how can we enhance the performance of generic large language models using fine-tuning strategies? And we also want to understand to what extent would the performance look like? So to answer the accuse, we developed a methodology in the context of mechanical component, CAD generation, and we selected 5 mechanical components representing different levels of complexity. And to fine-tune a large language model, we must have a training data set that contains data pairs associating the correct CAD programs with the corresponding input modalities that can include text, images, or sketches. So to achieve this, as shown in the figure on the right, in step 1, we first collect the CAD models of the 5 different mechanical components. And then we use GPT-4 as a debugger to help generate as many correct CAD programs as possible that can be translated into 3D CAD models later using a CAD kernel, such as CAD Curie. So the correctness of the CAD programs is evaluated against the ground truth CAD models. So the image data and the sketch data were collected from the CAD model directly and relatively easier from rendering and OpenCV. However, one challenge we faced at that time was to collect real human text descriptions. So for that, we used Amazon Mechanical Turk and published cross-sourcing tasks to collect natural language descriptions of the different mechanical components in varying dimensions. And each component has published 1,000 tasks and has a success rate of 60 to 70%. So here is a summary of the initial multimodal datasets for the CAD program or CAD code generation in Spring category and then Flange category as examples. So using the dataset, we used OpenAI's API and design a prompt using a persona technique to generate CAD programs or CAD codes. Like I mentioned earlier, so we use a large language model in this process as a debugger at the very beginning to generate as many correct CAD programs as possible for training purpose. And the purpose is trying to reduce, the debugging process is trying to reduce the syntax error. And the final CAD program is the format of CAD Curie, and then we use CAD Curie as a kernel. We tried different modality combinations, as you can see in the second column. And we used different GPT models, GPT-4 and 4V. Those models are most updated versions of the API available at that time. And we also tried different combinations with different debugging process. Then we adopted two metrics for evaluating the correctness of the tag programs. The first metric is the parsing rate. So basically, we evaluate the syntax error at the code level. And also, we used intersection over union to evaluate the correctness at the CAD model level. So with this process, we can generate many CAD programs. Of course, some of them won't work. Some of them are correct. And for training a fine-tuning model, once we have all the generated CAD programs, we used those whose parsing rate is 100%, which means the fully parsed, and intersection over union is greater than 98%, and as a program template. So these templates are basically all good CAD programs that can be translated into 3D CAD models later. So with these CAD programs, we substitute parameters with original data points to teach GPT models to generate programs that they could not previously generate correctly. So this will help us to get the training data pairs as shown in the next slide, in this table on the left, basically show the data pairs for the end-to-end training of the fine-tuning models. And during the investigation, we found that there was one interesting question. And because there are many different types of correct CAD programs, but in different length. So we asked the question, how does script length affect CAD generation outcomes? So to test this, we did experiments as follows, and we used 4 different sampling strategies, and we have 300 training data pairs for each strategy, and we test our fine-tuned models on 500 unseen data, and we fine-tuned a 3.5 GPT 3.5. That's the highest version at that moment 2 years ago that was able to be fine-tuned. So here are the 4 sampling strategies. We have the random selection, we have evenly distribution based on the script length. We have the selection from the shortest scripts and also selection from the longest script. So here the figure shows an example of the distribution of the code length following strategy 3, the shortest, and strategy 4, the longest. And you can see how they differ from the original data set from the GPT-4 models. And I also show example of how the short script and long script look like in general. So we tested all 4 fine-tuning models with different strategies and obtained some interesting results. So in the evaluation of the passing rate, we see that every fine-tuned model surpasses GPT-4 in blue bar. These are 4 green bars are for fine-tuning models using different sampling strategies. However, we found that longer script could negatively influence the fine-tuning performance. And if we compare the performance across different mechanical components in different complexities, we found that fine-tuned models, if you see the last 2 groups of data, have a worse performance in generating more complex components, for example, gears and the springs. However, we found that the improvement of the fine-tuned model is more pronounced. If you compare the blue bar, which is representing the performance of GPT-4 model, and those color bars of those 4 fine-tuned models. And we found similar results while we're evaluating IOU. I will not go into too many details, but basically we also see a longer script hinder accurate pattern learning and generalization, leading to increased syntax errors, as well as geometric errors. So to further test the fine-tuned model's generalizability and scalability, we chose 2 real-world components from the ABC dataset, is well-known dataset in the literature. And these are the 2 real-world components we picked, pillow block and arrange. And we tested 1 model. We tested a fine-tuned model 2, which trained on all the 5 original components using the strategy of evenly distribution sampling. And we got the performance in blue bars. And you can even improve the model by fine-tuning the previously fine-tuned model, right? So following the same strategy, same methodology as we just introduced. And you can see in the yellow bars, it shows how the model can be increased. And then there was a significant increase if you including the new data set into the fine-tuning strategies and further fine-tune the previous fine-tuned model. So lastly, I want to show some qualitative evaluation and some flawed geometries. And you can see different type of the geometries that was not able to be generated correctly, which indicates there's still improvement that can be made in the future if we have more data set. However, the methodology introduced in this paper is generalized that can be applied in different type of situations. So that's all my presentation today. I would like to thank the support from the NSF. And also, I would like to give credit to my current PhD, Yuewan Sun, and my prior PhD, Xingang Li. And you can download our dataset by scanning this QR code. Thank you, everyone.
Thank you, Jingwei. So with that, maybe we can stop the recording.
Yes.
Great, thanks, Chris. And Dr. Stephen.